Alright guys, let's go take a look at your inverse function test review. I gave this to you last week, and let's go ahead and put the answers down. This is the first question is a transformation question. Vector shift down by 2, horizontal shift 3 to the right, and a horizontal compression by a factor of 2. So how I'm going to start this, first thing I'm going to notice is this is y equals the square root of x. So I'm going to go ahead and jot down what that graph looks like. We have a little a dot here in the center of the origin, and this was going to go this way. This is what this graph looks like. You can't have a negative x value because you can't take the square root of a negative value, and because of that you won't get a negative y values either. So that's kind of a sketch of what that parent function looks like, but let's go ahead and hash out these transformations. So I'm going to say first that f of x is equal to x to the power of a half. That's the same thing as taking the square root of x. So the first thing I'll look at that I want to do actually is this horizontal compression by a factor of 2. So I'm going to say, okay, that's a transformation that's inside this parentheses. So let's say it's 2 times x now, which means we're going to change this x into a 2x. So this one as well, what this is going to mean is then this is going to be 2x to the power of a half. Okay, and I'm going to call that g of x as well. G of x is f of 2x. Okay, that's f of x up here. So that's one transformation. The second transformation I'll do is the horizontal shift 3 to the right. So I'm going to make another function here called p of x, and that's going to be g of x minus 3. Now it's important to notice that this shift is to the right. So when you're shifting to the right horizontally, you subtract instead of add, and you'll do this inside the parentheses. Horizontal transformations are inside this parentheses here for the function. They're changing the input basically. So what this is going to give me is 2 times x minus 3 raised to the power of a half, all of that whole thing. Okay, and the last thing we'll do is the vertical shift down by 2. So I'm going to say then, let's make h of x, that's going to equal p of x minus 2. And that's going to equal 2 times this to the power of a half, and then minus 2. So if I clean this up, all of these transformations together will give me this equation. If I go ahead and distribute this 2, okay, it's going to give me 2x minus 6 raised to the power of a half minus 2. This is the equation that I'm going to graph. Okay, and so I asked you for the equation and the graph, so let's go ahead and graph this. If I remember this parent function, it's going to usually starts here at the origin, but now we're going to shift down by 2 and to the right by 3. So I'm going to go 3 to the right and down 2. So it's actually going to start here now. Okay. Now that I've incorporated these transformations, I've already shifted down by 2 and I've already shifted to the right by 3. So what I really have here is just this 2 times x to the power of a half. That's all I'm really worried about now. Okay. So what I'm going to do is pretend starting from here it's a function 2 of x to the power of a half. If I plug in a 1 into this x, it'll be 2 times 1, which is 2, and 2 to the power of a half, which is a square. Let's not put in a 1. Let's put in a 2. That'd be better. So 2 times 2 is 4, and then 4 to the power of a half, which is the square root of 4. That'll be 2. So if I go 2 to the right on my x, I'm going to end up going 2 up on my y. That's what I'm saying. If I plug in 2 here, 2 times 2 is 4, and 4 to the power of a half, or the same thing as the square root of 4, will be 2. So this is my frame of reference here, my reference point. I'm going to go over 2 and up 2, and I'm going to be right here. So this graph is actually going to go off this way, even though I can't draw it very well. And yeah, it's going to probably be a little higher than that, like this. And it's going to go off that way like that. So yeah, let's fix that if I can. I can erase that and draw that better. So we said 3, 2, and then here. Something like that, okay? And let's go ahead and check this in a calculator. You don't get a calculator, so we're going to basically just prove this work. It makes sense using a calculator. And I'm going to keep in mind these points here. This point here is 3, negative 2. And this point here is 1, 2, 3, 4, 5, and 0. Okay, let's go and make a quick graph of that. It's going to be 2x minus 6 all raised to the power of half, which is the same thing as taking the square root, by the way, and then minus 2. So that's the graph we get, and we will find that 0 just to make sure. So I'm going to do analyze graph, find that 0. That should be 5, 0, and it is, just like I said it would be. And that's kind of what the graph should look like after all your transformations. Okay, so just some proof for you, that's all. Alright, let's continue. Okay, next question, a vertical shift up by 2, horizontal shift 1 to the left, and a vertical stretch by a factor of 4. This is a line, so this is pretty straightforward. Y equals x is the parent function of all lines, and it goes like this. It just goes right this way and down this way. Okay, very straightforward parent function. We're going to say f of x then is equal to x. Same thing as saying y equals x. And then the first thing I'm going to apply is this vertical stretch by a factor of 4. So I'm going to make another function here called p of x, and we're going to say that's 4 times f of x. Okay, or this, 4 times this, which is basically 4 times x, which is 4x. Alright, so that's one transformation as a vertical stretch. Vertical stretches and compressions go outside of the function, okay, put in front. So the horizontal shift, we'll apply that next. That's 1 to the left, so I'm going to say h of x is going to equal p of x plus 1. That's a shift to 1 to the left. And what that's going to give me is, in fact, 4 times x plus 1. Okay? Since p of x is 4x, then p of x plus 1 is 4 of x plus 1. That's pretty obvious. Now the vertical shift up is the last transformation, so we'll call that one g of x. That's going to be equal to h of x plus 1. So what I have now, since h of x is 4 times x plus 1, I have 4 times x plus 1 plus 1. Okay, if I simplify that, g of x is in fact equal to, if I distribute this 4 actually, it'll equal 4x plus 5, because 4 times 1 is 4, plus 1 is 5. So this is actually the equation we're going to graph after all these transformations. It's just a line. So we're going to start here at 5. I'm going to go up 1, 2, 3, 4, 5. And it's just like we graph any other line in mx plus b form. And I would usually say go up 4 and over 1, but I can't do that since I'm out of graph. So I'll go down 4 and backwards 1, which is the same thing. So I'll go down 4, backwards 1, and I'll connect a few of these points. Alright, and then I'll try to sketch a line with this pen. Yeah, not perfect, but that's how I'm doing this here on the smartboard. So there you go. And that would be that answer. Here we have the parent function of the absolute value of x. So we're going to say, what does that graph look like? The absolute value of x, it looks like a V that's going from the origin. Okay, so let's go ahead and write our transformations. F of x is now the absolute value of x. I got a vertical shift, a horizontal shift, and a reflection across the x-axis. Okay, let's go ahead and do the reflection first. The order in which we do these doesn't matter a whole lot, but let's just do the reflection first. So I'm going to say P of x is going to equal negative f of x. That's how you reflect across the x-axis. You put a negative in front of the function. So since f of x is absolute value of x, then that's going to be the negative absolute value of x. That'll turn this graph upside down, basically, reflected across the x-axis. Let's apply the horizontal shift 4 to the right. So I'm going to say g of x, or h of x I should call it, h of x will equal p of x, but since it's going to be shifting 4 to the right, it's going to p of x minus 4. And since p of x is this function, that's the same thing as saying negative of x minus 4. Negative absolute value of x minus 4. And the last thing we'll do is the vertical shift down by 2. So that'll be g of x, and that'll equal h of x minus 2, which is the same thing as the negative of the absolute value of x minus 4, and then minus 2. So that's the function we're going to graph when it's all said and done, is this. Okay, so it's this function here, we move it from the origin 4 to the right and 2 down. And that's our point, and since we're reflecting upside down, it's literally going to go down 1 over 1 this way, and down 1 over 1 this way, and you'll get a graph that looks something like this. Okay, and that's your function and your graph for that question. Alright, let's turn the page. Alright, we've got a couple more of these. So here we got a vertical shift down by 2, reflection across the x-axis, horizontal compression by a factor of 2, so there's a lot going on. So let's figure out this parent function. I like to sketch what they look like just in the corner over here. The function x cubed looks like this. Okay, it makes a little S pattern here, or not an S, but like some students call it, a snake-looking graph. So let's go ahead and start these transformations. I'll say first f of x is equal to x cubed. Okay, let's do the horizontal compression by a factor of 2 first. So that goes inside the parentheses. So I'm going to say p of x is going to equal f of 2x now, right? Which means we're going to turn this x into a 2x. So that's inside the parentheses, 2x all cubed. Very important that you put the 2 inside the parentheses. So that is your horizontal compression by a factor of 2. Horizontal transformations, compressions, and stretches go inside the parentheses. Reflection across the x-axis, we'll do that. We'll say that called h of x, and then all we're going to do is say that's the negative of p of x. And p of x, since this is the same thing as this, it's the negative of 2x all cubed. Okay, and then the vertical shift down by 2, very straightforward, g of x, and that'll equal h of x minus 2. And that'll give me this equation, 2x cubed minus 2. So our final graph, g of x, will look like that, negative 2x cubed minus 2, and we have to graph this. Okay, so what I'm going to do is I'm going to apply these two transformations first. I'm going to apply this negative 2 and this negative out front. So negative 2 is just going to take the parent function and drop it here. Okay, usually it'll cross here at the origin, and now it's going to cross 2 lower than that. So this is accounted for right here. I've accounted for this. The negative is going to reflect the graph across the x-axis. So while the graph usually would go up in this pattern, this way, now it's going to come across this way instead. So just keep that in mind. So now I'm just going to plug in a value starting from here. I want to go 1 over, so I'm going to go to negative 1. I'm going to plug in negative 1 just into this part right here. That's all I'm focusing on. Okay, I'm ignoring the negative and I'm ignoring this. I'm just plugging in negative 1. Negative 1 times 2 is negative 2. And negative 2 cubed is negative 8. Okay, so if I go 1 over from here, I'm going to go down 8 spaces. So 1, 2, 3, 4, 5, 6, 7, 8 off the graph, but down here somewhere. Okay, I would say that, but actually that's not true because I reflected this, right? So this is actually going to be going this way. Okay, it's going to go down 8 this way, actually. Alright, so let's ignore this part. And we're going to say here, if I plug in, let's say I plug in a positive 1, that'll give me 1 times 2, which is 2, and then cube that, which is 8. So remember, positive 1 is going this way since I've reflected it, so I'm going to go up 8 this from here. Starting here, so I got 1, 2, 3, 4, 5, 6, 7, 8. So this. So what I actually have is a steep graph, and I don't even know if I'm going to draw this that well. And it's going to go kind of like that. Alright. It's not perfect drawing, but it's a good rough approximation for the sketch. And that's what this graph will look like. The reason that this graph is going this direction instead of this direction is because of this negative out front. So it's important you know that. Okay, so if you were to graph that, that's kind of what it would look like, even though that drawing is far from perfect. So let's do number 5. This is another line, so we know the parent function again. We've already talked about this. It just goes right through the origin. Okay, and we're going to do some transformation. So f of x is equal to x. Go a little faster, so we're going to say p of x. First thing I'll apply is a horizontal shift to the left, so that's going to equal f of x plus 4. It's going to the left, so we add. Okay, and that's going to equal basically x plus 4. And then I'm going to flick across the x-axis, so we're going to say h of x is negative p of x. So that's going to equal the negative of x plus 4. And then the vertical shift up, that'll give me my g of x we can use. And that'll equal h of x plus 2. That's a vertical shift up by 2. So this will equal the negative of x plus 4 and then up by 2. So this final equation, you could write it as that, negative x plus 4 plus 2. Or if you distribute this negative, we could write this actually as negative x, and then negative 4 plus 2 would be negative 2. You can write it this way if you like. These are the same. Okay? So let's graph that really fast. We start at negative 2, and the slope is negative 1, so we go down 1 over 1. So here, 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 so on and so forth. Alrighty. And if I actually were to try to draw this, not so perfectly, it looks something like that when I graphed it. Okay. Last transformation. Thank goodness, right? And then we have y equals x squared. So this is the parabola. The parent function of the parabola goes like this. So we'll start off with f of x is equal to x squared. And then we'll do a horizontal stretch by a factor of half. Horizontal stretches and compressions are inside the parentheses. So p of x is going to equal f by a factor of a quarter, I should say. A fourth x, right? So that means this x is being replaced by this. So keep it in the parentheses is 1/4 x, and this is all squared. All right, and then we have a vertical shift down by 2. So we'll just call that g of x then. That's equal to p of x minus 2. So that'll equal 1/4 x all squared minus 2. So we'll rewrite that g of x. If I actually square 1/4 x, 1/4 times 1/4 is 1/16. And then I'll have x squared minus 2. This is actually the equation we're going to graph. Okay. And let's take this. We're going to say usually we'll start at the origin, but now we're going to shift down by 2. So that's our starting point. So we've accounted for this. Now we're just going to focus on this part. Okay. So if I plug in 1 in x, I'm going 1 this way. If I plug in negative 1, I'm going that way by 1. Okay. But I see this as a 16th, and I have a square here, so I actually want to plug in 4. If I plug in 4 here, 4 squared is 16. Okay, so plug in 4 for x, and then 4 squared is 16, and 16 times a 16th is 1, which basically means if I go over 4 this way, I'm going to go up 1, just like that. If I plug in negative 4, I'll square that, and then it becomes positive 16 again. and then multiply that by 1 over 16, and that's also 1. So if I go negative 4 this way, I'm going to go up 1 as well. So what I end up getting is a parabola that's kind of opening up quite widely here in this fashion. This is a terrible drawing. Okay, but let's try this. Yeah, it's going to look something like that. So you have a parabola that's opening upward and it's going quite wide. All right, so there you go. That is, sketch like that would be fine. And then we're going to go on to the next question. All right. Find the inverse equation of the following function, graph the original function and its inverse. All right, so let's actually graph this function really quickly. This is negative 4. And I'm going to go up 1 over 2 for the slope, which is here, 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 here. And I'll try to draw this again, which is not easy to do, but do our best. Okay, so we graph this function, check. Graph the original function, no problem. And the inverse. So let's find the inverse. Let's take this x and y value and flip them. Flip and find. So we'll say x is now equal to 1/2 y minus 4. And then I'll add 4 to both sides of this equation. So I'll say x plus 4 is equal to 1/2 y. Okay, when you multiply by half, you're dividing by 2. So the opposite of dividing by 2 is to multiply both sides by 2. And that's what I'm going to do. So I'm going to say this times 2. 2 times 1/2 is 1. So it's 1y. And then we got this, which will distribute. So we have 2x plus 8. And we will call this our inverse function right here. All right, they want me to find the inverse equation, so I did. And we defined the graph for it now. So we'll just do that. We'll go up 8. 1, 2, 3, 4, 5, 6, 7. Right off the grid here, about here. That's where the intercept is, 8. I can't go up 2 and over 1, so I'll go down 2 and back 1 since I'm off my grid. I'll go down 2 and back 1, down 2 and back 1, and it will look something like this. And then we'll see what we can draw. Okay, these two graphs will intersect, and this is a reflection, as you know, across this line here, which is y equals what? Y equals x, remember. So I don't require that you draw that, but I want you to see that that's a reflection across y equals x. Every time we do an inverse function graph, it'll be a reflection of the original graph across y equals x. It says find the domain and range of the original function and the inverse. Here's the original function right here. So they want the domain and range of that, and that's pretty easy for a line. This is going to go forever in this direction, and it's going to go forever in that direction for the domain. So this original function f of x will have a domain from negative infinity to infinity in integral notation, and the range will be the same, from negative infinity to infinity. It'll go down forever and up forever. The inverse function is usually easy to find after you have the domain and range for the original, because you just take the domain and range and you flip them. So it'll be the same, actually. It won't look any different for this particular graph. And the range as well. Okay, it wants to know the end behavior for the inverse. Remember, this is the inverse right here. Let's change the pen color here. And let's do that. So if I go in this direction forever, x will go to negative infinity. And then what's happening to the graph as I go this way? It's going down. The y value is going down also to negative infinity. So that's worth noting. So I'll start off with that. I'll say the end behavior of this function and say f of x is approaching negative infinity as x approaches negative infinity. In the other direction, if I go this way and this way, I'll see f of x is going up as x is going to the right. So then I'll say f of x is going up to infinity as x moves to the right to positive infinity as well. And that will be my end behavior for the inverse function. Just do the inverse function. That's all they asked me for. Okay, so let's move on to number 10. Find the inverse equation for the following function, graph the original function and its inverse. Yeah, we're going to do this all over again. So let's change my pen color 2 purple. This is a cubic function, and it's shifted right by 3 and up by 2. Cubic function usually has its center at the origin. So we're going to go 3 to the right from there and up by 2. So this new center is going to be right here. Okay? Then I'm just going to cube this, basically. So if I plug in, after I accounted for these transformations, now what I'm basically looking at is a function x cubed. So if I plug in 1, I'm going to go 1 over that way. And I'm going to cube it, which means 1 cubed is 1. So if I go over 1, I'll go up 1. If I plug in -1, which means I'm moving from here over this way, I'll have -1 cubed, which is going to be -1. So if I go over 1, I'm going to go down 1 this way. And I got this going on here. Okay. And if I go over 2 and cube that, I'll go up to 8. So if I go over 2 from the center here, I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8. It's going to be quite high, somewhere up here. From the center, if I go 2 this way, I'm going to go down 8. So if I'm going to go down 1, 2, 3, 4, 5, 6, 7, 8. So what this graph is actually going to look like is something like this. It's going to go up quite steeply. And this is not a good drawing, okay, but the best I can do with this pen. And it's going to go kind of like that, okay. That's this original function. Let's find its inverse. But before we do that, let's go ahead and graph the inverse. I actually don't need the equation to graph the inverse once I have the original equation down. So now that I have the first graph, let's graph the inverse, and let's make this blue, I guess. So I'm just going to look at some of these points I have. I have 3 and 2, this coordinate right here. So if I take 3 and 2 and I flip the x and y value, I'll have 2 and 3. So now I'm going to go over 2 and up 3. So this point is going to be translated over here. This point I have 2 and 1, so now I have 1 and 2, which is translated here. This point is 4 and 3, so now I have 3 and 4. Over 3 up 4. So we translated this point, this point, this point. This point right here is 1 and -6. So now I need to go over to -6 and 1, which is right here. So what I'll get at the end of all this is I'll get this little thing here, this sort of graph that's going to do this when I graph it. And what you should see is that this also, again, is a reflection across y equals x. Okay, it should pretty much look like this all the time for inverse functions. Okay, so that's your graph, but we found the graph of both equations, but let's go ahead and write the inverse equation. So let's look at this equation and flip the x and y again. So we'll say x is now equal to y minus 3. Y minus 3. Ooh, it's really awful. Let's get the eraser. Oops. Helps if I actually select it. And we rewrite that. The y minus 3 cubed plus 2. So I'll subtract 2 from both sides to start with. So x minus 2 will equal y minus 3 cubed. And then to get rid of this cube, I'll take the cube root of both sides. So I'll say the cube root of x minus 2 is now equal to y minus 3. And then I'll add 3 to both sides. So y will equal the cube root of x minus 2 plus 3. And that will be your inverse equation right here that we have. Okay? That is number 10. So let's move on to number 11. Find the domain and range of the original function in the inverse. Okay? This is going to be very much like the first example we did just above. We're going to say f of x has a domain and range, of course. But the domain, this is the original function, this graph is going to go this direction forever, even though you can't really tell. And this is going to go down forever. We know that's how x cubed behaves. So the first thing I'll say, well, that's in behavior. First thing I'll say though is that the domain and the domain is going to go forever this way, and it's going to go forever this way as well. So the domain is going to be -infinity to infinity. The range, this thing is going to go down this direction forever and up toward infinity forever. So we got this again. For the inverse function, have the domain and range as well. It's the same thing as these that flipped around. So this is going to go forever this way and forever this way. So that domain is also negative infinity to infinity. And this green graph will go down this way forever and up this way forever. So it's also negative infinity to infinity, which is the same as these two flipped. Okay. And the end behavior of the inverse equation, which is this green graph, we just said that. We talked about the direction it's going this way forever and down. It's going to go down as it goes to the left. So we'll start off by saying that f of x will approach negative infinity as x approaches negative infinity. And that f of x on the other side will go toward positive infinity as x goes to positive infinity. And that's kind of what that's going to do on number 12. So let's turn the page and let's work on some familiar stuff. We have complete this following function operations. Alrighty. Okay, so these are called composites when you see this little circle inside of here, and basically it just means plug in -2 into g. So that's my g function right here. This x is now going to become a -2. So g of -2, goodness me, why is it doing that? G of -2 is going to equal 2 times -2 minus 3. -2 minus 3 is -5, but the absolute value of -5 becomes a +5. So what this is going to, this part's going to give you 10. 10 is now going to go into h. So right here, this x value will be a 10. So 10 minus 3, okay, so we'll say h of 10, that's going to equal 10 minus 3. This answer will be 7. Because this -2 and this 7 don't match, we're going to say these two functions are in fact not inverses. Okay, I actually probably don't want you to indicate this on the exam, but since I wrote it in the instructions, we'll go ahead and do that. They're not inverses because these two numbers should be identical if they were. Okay, we're going to plug in 2 and h on this one. So again, we got here h of 2. We got 2 minus 3 now. That's going to give me -1. And that's going to go into the g. So we have g of -1 now. Remember, this is going to go this way. And that's going to go into this x. So this is going to equal 2 times the absolute value of -1 minus 3, which will equal, since -1 minus 3 is -4, the absolute value becomes +4. It's 2 times 4. So this answer will be 8. Okay, these two, again, don't match for this composite. Remember, this only counts for detecting an inverse if you have a composite function, and because these two answers are not the same, these again are not inverses. Just to be consistent. So let's keep going. We'll plug in 1 into g here, so we'll say g of 1, and that's going to give me a 1 in there, so it's going to be 2 times 1 minus 3, the absolute value of 1 minus 3. And that will become a -2, and then it becomes positive after you take the absolute value. So it'll be 2 times 2, basically, which will be 4. And that'll go into p now. So I need p of 4. P is this quadratic equation. So I got 2 times 4 squared minus 5 times 4. Substitute in for x, right? And then minus 3. 4 squared is 16 times 2, that'll be 32, minus 20 minus 3. 32 minus 20 is 12, and 12 minus 3 is 9. And that will be your answer. Okay. Now we're going to move on to this one. X will go into h. So we already have that, h of x. So we'll say h of x is x minus 3. This right here will be the input for p, and p is this quadratic up here. So now I have p of x minus 3, and that'll equal 2 times x minus 3 squared minus 5 times x minus 3 minus 3. Alrighty, check the time here. 6:30, good. Alrighty. And we'll go ahead and say, what is x minus 3 times itself? X minus 3 times x minus 3. So I'm just going to go sketch this right over here. I'm going to say that's equal to x squared minus 6x plus 9. That's what happens when you multiply these together. So what I have here is 2 times x squared minus 6x plus 9. And then I have this negative 5 I'll distribute, so that'll be minus 5x and plus 15, and then minus 3. I'll go ahead and distribute this 2. I'll get 2x squared minus 12x plus 18 minus 5x, 15 minus 3 is plus 12. We'll combine like terms and we'll be finished. So I got 2x squared. That's done. Negative 12 minus 5 is negative 17x. And then 18 plus 2 is 30. So this is your answer for that question. Alrighty, keep going. This one usually pretty tricky. P, what this translates to is P of x divided by H of x. Okay. Now P of x, we can see from the page there, that's going to be looks like 2x squared minus 5x minus 3. This will be divided by x minus 3. Okay, so we're going to say we're going to multiply. I told you guys when you have a coefficient that's not 1, this is kind of tricky to factor. So the trick I use is I'll multiply this first one by this last one. And I'll say 2 times negative 3 is negative 6. Okay, now I got this negative 5x that I'll just keep over, and then I have the x squared. Now what I do when I do this is I transform this 2 into a 1. This makes this easier to factor. So what are the factors of negative 6 that add to make negative 5 is kind of what I'm asking you here. And those factors are what? That'll be negative 6 and positive 1. Now these aren't the real factors because when I multiply these two I change the problem. So now I'm going to change it back. I'm going to divide these two numbers by this number I had in front here, which is a 2. So this will give me x minus 3, which is a real factor, and the other factor is x plus a half. I can move this 2 on the bottom up front if I can't reduce this fraction. This will give me 2x plus 1. So this whole thing right here gave me these two factors. And on the bottom I still have what? X minus 3. So what happens is these will cross out, and then your answer is what's left. It'll be 2x plus 1 for that. Okay. Here, go for this again. We're going to say this is going to be x minus 3. It's the same thing we already had. And we're going to plug that in f. So now I have f of x minus 3. So this is going to go into here. And let's take a peek at what f is. And that's going to be negative 3x squared minus 6. Okay, so it's going to be negative 3x minus 3 squared minus 6. And then we have this again. I think I've already found this though, which is a great thing, because I've already done x minus 3 squared. I did it right here. So we have this, we're going to reuse. It's going to be x squared minus 6x plus 9. And then we'll subtract 6. I'll distribute in here, and then I will simplify. Okay, so this is going to be negative 3x squared, and then positive 18x, and then negative 27, and then minus 6. So this will give me negative 3x squared plus 18x, and then 27. Negative 27 minus 6 is negative 33. And that will be your answer for that. Okay. So let's move on to number 19. Should be running out of questions pretty soon. Hope anyway. Find the relative extrema. So this is the derivative questions. So we'll take a derivative of this and we'll set it equal to 0. All right. So we're going to say there's a 1 here. 3 times 1 is 3, and then we'll take 1 from the power, which is 2. 2 times negative 2 will be negative 4. We're multiplying the power by the coefficient, and then take 1 off the power. The derivative of 3 is nothing, so this is going to equal 0. The reason we set it equal to 0 is because if I had some imaginary graph like this, okay, this derivative is telling me the slope of a tangent line. And tangent lines are all over this graph. Some of them will have negative slopes, some of them will have positive slopes, but at the extrema, the minimums and maximums, the slope of the horizontal line will be 0, which is why I'm setting this derivative equal to 0, because if I can solve it for x, it'll tell me the x values for these extrema right here, right? So let's go ahead and set this equal to 0, but I'll factor this. What can I factor out of both of these? I can factor out an x for sure. So I can take out an x. That'll give me that. So I can say that's going to give me 3x and then minus 4. If I set both of these factors equal to 0, okay, then I'll have x equals 0, and I'll have 3x minus 4 equals 0. If I solve this for x, x is going to equal 4/3. So basically what I'm looking at is we got this right here, and this right here is my potential solutions here. These are my extrema locations. But what's a maximum, what's a minimum, which one is which? So I have x equals 0, I have x equals 4/3, and I'll use my number line to figure it out. So if I plug in 0 or 4/3 into the derivative, I'll get 0 back. That's what this means. If I plug either one of these values into this, I'll get 0. Now I have to figure out, since I know where that's 0, what is it? If I have a pick a point below it and above it, will it be positive or negative? It'll tell me basically if this is a minimum or maximum. So I'll pick a point like -1, and I'll pick a point here like +1, and another point here like 2. Okay, and I'll plug in -1 into this derivative. So if I plug in a -1 here, I'll have a negative for the x. If I plug in -1 here, it'd be -3 minus 4, which is another negative. A negative times a negative is a positive. So the slope on this side of -1 will be, it'll be going up, it'll be positive, all right? If I plug in 1 into here, I'll get a positive, and then 3 times 1 is 3, minus 4, that'll be a negative. So a positive times a negative is a negative. If I plug in 2, I'll get a positive, and then 3 times 2 is 6, minus 4, that'll be another positive. So that'll give me a positive. So from here I go up and then down, so this 0 is a maximum. From here I go down and then up, so this 4/3 is a minimum, we'll say. And that will be your answer. That's how you do these, okay? And there's only 2 more of those, so let's go ahead and hash it out. P of x, P prime of x, we're going to say 2 times 2 is 4, take 1 off the power. This is 1 here, 1 times -4 is -4, and that's it. That's the derivative, okay? There is no constant at the end. So we'll set this equal to 0. 4x minus 4 equals 0. As long as there's only going to be one answer here. So that means 4x is equal to 4, and x will be 1 when I solve it. Okay? So is 1 a minimum or a maximum? Well, we can tell this graph is a parabola. And because this number is positive, it's going to open upward. This should be a minimum, but let's test it anyway, just for the sake of, boredom. And we'll say 1. We'll plug it in there into this derivative. 4 times 1 is 4 minus 4, which is 0. So that means this would have given us a 0, as we knew it would. And we need to pick another value below it and another value above it. So we'll say plug in 0 here. So 4 times 0 is 0 minus 4, that'll be negative. If I plug in 2, 4 times 2 is 8 minus 4, which is 4, and that'll be positive. So if I go down and up, this x equals 1 is in fact, as I said, a minimum point, and that's the only one you get, because that's basically the what? That's the vertex right there at what? At x equals 1. That's the vertex of the parabola. Okay, call it that, the vertex. All right, let's go down here, and we'll say the derivative of this, and we'll say that's a -1 times 4, which is -4, x to the power of 3 now. 2 times 2 is 4, x to the power of 1. The derivative of a constant, of course, is 0. and we'll set this equal to 0. Can I factor this? Yes, I can take out a -4 and an x for sure. So -4 and x. What do I multiply this by to get this? I will multiply it by x squared. What do I multiply this by to get this? I will multiply it by a -1. Okay. And then we'll set both of these factors here. Both of these factors equal to 0. So -4x equals 0, and x squared minus 1 equals 0. That means x is going to equal 0 here, and here it means x squared is equal to 1, and the square root of both sides, x will equal plus or minus 1. So what I really have are three answers. I have a -1, a positive 0 rather, and a +1. And we'll test all three of them. These all give me slopes of 0. So we'll pick a value less, another value in between, -0.5. We'll pick a value here, +0.5, and 2. So there's a lot of testing going on here. We've got to test a lot of these points. So we'll plug in -2 in here. That'll be a negative times a negative, which is a positive. -2 squared is 4. That's also a positive when I subtract 1. So that'll be positive. If I plug in -0.5, that'll give me a positive. And then if I square a half, that's going to give me a fourth minus 1. That's actually going to be a negative. So what I now have is a positive and a negative, which is a negative. If you plug in a +0.5, that'll give me a negative here. And then a +0.5 again is going to give me a fourth, and that's going to give me another negative. So a negative times a negative, this time it'll be a positive. If I plug in 2, that'll give me a negative and a positive. And that'll give me a negative. So at -1, I'm going up and then down, so this is a maximum. At 0, I go first down and then up, so that is a minimum. And then at 1, I go up and then down again, so that's another max. And these are my relative extrema. All right. And let's keep moving. Oh, there's nowhere else to go. Looks like I'm done. Okay, looks like I had 21 questions on that review, and there don't appear to be any more questions on there. So that's fantastic. Okie dokie. I appreciate you watching this. I hope it's helpful. Make sure you come in and ask questions in tutoring hours if you have them. But I hope this is, this is useful. We've done many problems like this in class already, so you should be pretty well prepared, and I'm sure you'll do fine. So thanks for watching, and good luck to you. Appreciate it.